Okay, welcome to this lecture. Last time I left you with the task of thinking about the multi-wavelength Milky Way view that I left you with last time. So if you haven't done so already, then please go and have a look at that. There's the link to this. This is the website linked to those set of pictures and data, and there are some explanations there as well. If you once you've thought about it yourself, you can go and have a look there. So that's linked off the web resources in Minerva. Also, don't forget, if you haven't done so already, as part of Workshop 4, there were these multi-wavelength views of M101 Galaxy. This is just 3 of them. There are 6 of them on the Workshop 4 website to have a look at. And again, same idea. Think about why the same galaxy looks different, so different in different wavelengths, and try and understand that. That's a key part of this course. Okay, so today we are looking at, we've been introducing the idea of galaxies and the interstellar medium. Now we're going to look at what happens when galaxies interact with each other, and this also leads us into the sort of exciting field of so-called active galaxies, and will lead us to supermassive black holes as well. So, previously I talked about galaxies as being, reasonably isolated. We've talked a little bit about companion galaxies like the Large Magellanic Cloud, Small Magellanic Cloud around our own galaxy, and we've seen the 2 little elliptical companions of the Andromeda Galaxy. But here, let's now think about what happens if you get 2 large galaxies, like 2 large spirals, and get them to collide. So it's not actually uncommon, okay? A way to think about this a little bit is to think about the relative size of a galaxy compared to the relative separation between galaxies, okay? So we saw last time that the sort of total scale, if you like, of the Milky Way galaxy, which is very typical, would be about 100 kiloparsecs or something of that order. Whereas the next nearest galaxy, so the Andromeda Galaxy, which will also be similar in size, is about 1 megaparsec away, okay, so, or 1,000 kiloparsecs. So that's only a factor of 10 between the size of a galaxy and the typical separation between 2 galaxies. So that's not actually that high, okay. If you compare that to the typical size of a star, like the Sun, compared to the typical separation to the next star, then that's a ratio of 10 to the 6 or so, I think, maybe more, 10 to the 7. So it's that sort of ratio tells us that as galaxies are also moving around out there in the universe, then the chances of them colliding is a lot higher than the chances of stars moving around a galaxy colliding. So what happens? Well, again, we'll see this in some pictures in a moment. So you'll see that you get things called large tidal tails. So when you get extended sources of mass, like a galaxy together, and they are in the gravitational influence of another galaxy nearby, then the part of the galaxy that is nearest to the other galaxies sees a stronger gravitational pull than the far side. So that sets up a gradient in gravity across the galaxy, which basically rips it apart. So that's the effect of gravity in these gravitational interactions, is that it tends to tear the galaxies apart initially, and so that's what results in these so-called tidal tails that we'll see in a moment. And often galaxies tend not to really smash directly into each other. They sort of come into orbit around each other first and then spiral in towards each other, and before it all gets smashed up. So when this happens, as I was just trying to elucidate, then you might think two galaxies colliding is a bit of a calamitous affair, but for the stars in each of the galaxies, and to be honest, probably the planetary systems as well, probably won't make much difference. So the chances of two stars colliding, even when you've got whole galaxies worth of stars moving through each other, in effect, because of the relative small size of a star compared to the spacing between the stars, the chances of actual stars hitting each other is negligible. So there's not really that much effect directly on the stars. What does get affected is the gas. So here we're talking about really colliding gas-rich galaxies together. So either spirals or irregular galaxies that have got plenty of gas in them. So plenty of interstellar medium. So those gas clouds, when they collide, they can't move through each other easily. And they are large, of course, as you've seen. They cover a big volume of interstellar space. So inevitably, the clouds of gas basically hit each other and they get shocked and compressed. And if you compress interstellar gas, then the chances are you're going to start causing it to turn into stars, because once you compress gas, you increase its density, it's likely to then form more stars. And of course, this kind of collision between galaxies is happening in a relatively short timescale. I mean, you could think about how you might calculate such a timescale. I'll give you an example a little bit at the end as well. But it's a relatively short time frame in the cosmic span of things, and so that's going to lead to a lot of stars all forming at the same time. So this is referred to as a burst of star formation, or more commonly called a starburst, and you will see the term starburst galaxy. But again, it's usually not just one galaxy. It's as the result of some kind of collision or nearby galaxy activity. So this is much easier to explain if we see some pictures. Okay, so here is a very famous pair of interacting galaxies. These are called the antennae galaxies because of these kind of structures that you can see coming off here. And these are tidal tails. Okay, so these two galaxies, again, you can see that they've probably coming in, and they've probably done an orbit or two of each other a little bit, and they're in the process of getting very up close and personal. But all these gas and stars here has already been ripped out of each of the galaxies because of the way they are sort of interacting with each other gravitationally. So these are the tidal tails. Okay, so let's zoom into the middle there and see what's happening. Okay, so this is an optical picture from the Hubble Space Telescope, and you can clearly see that there are two spiral galaxies here. You can see the bulge of one with the red light here, and you can see the bulge of the other one here. Okay, and you can see that they've got spiral arms here and here, but they're already getting very disrupted. So you can see everything's getting sort of messed up. So here is obviously where the sort of action is at the moment, with a lot of interstellar clouds colliding together. So you can see a lot of dust from the interstellar material. But you can also see a lot of these red regions here, and also activity has been increased in this spiral arm over here. So this is the idea of H2 regions, so lots of young massive stars all forming at the same time here. So these are the bright H-alpha emission from the nebulae H2 regions. So a lot of massive stars all being formed at the same time in this interaction. And again, if we want to, hopefully, as you've been learning, if you want to sort of see through the dust and see where new stars are forming, you can go to the infrared, and if you go into the mid-infrared, you're really looking at the hot dust associated with where new stars are being formed and heated up by those newly born stars. And you can see again, all through this arm and all through this interaction region here is where all these new stars are being formed in one great big burst. Okay. So that's the idea there. Here's another nice example, referred to as the tadpole galaxy for obvious reasons, but this is another tidal tail. Okay, so you can see the stars in here. It's not just gas, it's stars that have been pulled out of their parent galaxy because, again, you can't really see where the two galaxies are now. They're already in a fairly advanced state of merging. There's stuff going on all over the top. This might have been a smaller one coming into this one, probably here perhaps. But again, you can see the effects of gravity pulling these galaxies apart. Okay. And for those of you who are at Workshop 4, we saw a lot of this kind of disrupted galaxies in the Hubble Extreme Deep Field image that you were looking at. Okay. And one last example here. Sometimes, even when you think galaxies aren't interacting, they are. Okay, so on the left, you've got an optical picture of 3 galaxies. And if you just looked at this, you wouldn't think necessarily that there was any interaction going on. You can't see any disruption here. There's something a bit weird going on here. We'll see that one a bit later. But if you go and look at the atomic hydrogen instead, so this is, again, recall, this will be your 21 centimeter emission line that is used to make this map of where all the atomic hydrogen gas is. And also recall that the atomic hydrogen gas extends usually quite a bit further than where the stellar disk of a galaxy, of a spiral galaxy is. And you can clearly see that here. The gas is extending way out. And when you look at the gas that's further out, you can see that clearly there are tidal tails of hydrogen gas linking actually all 3 of these galaxies together. Okay. So all 3 of these galaxies are in the process of interacting with each other. And this one up here, we shall come back to in a moment, is extremely clearly a very active galaxy at the moment. And one more view, this is another mid-infrared view. This is in a more sort of advanced stage where the spiral arm activity, it's clearly been disrupted, but it's also extremely bright in the infrared. So a lot of star formation going on here. So this will have had some kind of encounter that is leading to more star formation. Okay, so let's now think that through for a moment. So you've had a collision between 2 galaxies. Their interstellar clouds have kind of got compressed and started forming a whole bunch of massive stars all at the same time. So in a few million years, after that collision has occurred, those massive stars are going to start exploding as supernovae, because the most massive stars only last for a few million years. So that, again, that's a fairly short timescale. So during this whole collision process. But here, unlike a sort of normal galaxy like our Milky Way, where you've got one supernova going off every 30 years or so, here you're going to have them all going off, thousands of them all going off at pretty much the same time. Okay, and also in a very sort of fairly confined space as well. So that is like, setting off a huge set of bombs in the middle of the galaxy, effectively. And so the combined effect of all those supernovae explosions and the supernova remnants expanding out, merging into each other, so you end up with these huge bubbles of very hot gas that merge together. They will have an effect of sweeping gas ahead of them and basically blows the gas out of the galaxy. And so that's referred to as a super wind, okay, because it's like a wind, right? All the gas is being blown out of the galaxy by the explosions. So it will literally leave the galaxy. The gas will leave the galaxy entirely. It can't, the gravity isn't enough to keep it there. So this will have a dramatic effect on the galaxy's future, because you've actually now removed all of the gas, which is the fuel for star formation. So you've had this one great big burst of star formation, but then the death of all those stars at the same time basically strips all the gas out of the galaxy, or it can do. And that means that galaxy will then no longer be able to form any more stars. Okay, so it's left bereft of any fuel for new stars. So the stars that are left behind will just start to age, okay, and you're left with a galaxy with no interstellar medium. And of course, during the interaction, if you have two spiral galaxies, all their orbits will have got messed up. So the stars, individual stars, will now be just orbiting around the center of mass in any direction they want. So there's no organized rotation either. So all of those properties sound exactly like the properties of an elliptical galaxy. Okay. So an aging stellar population, no interstellar medium, and no organized rotation. So the merger of two gas-rich galaxies will end up forming an elliptical galaxy, is the idea. Okay. So we can see the superwinds in action. This is that galaxy. This is M82, the one I just referred to in the three galaxies, the top one. And if we look closely at this in a multi-wavelength picture, the green here is the optical sort of light. So that's the sort of discish light structure of the galaxy. But superimposed here in blue is X-ray emission. So this is showing us where there is extremely hot million-degree gas. So basically the kind of gas in a supernova remnant that is hurtling along at hundreds of kilometers per second. The red here is sort of H alpha, so that's, you can see that the sort of more normal interstellar medium is being pushed out of the galaxy here, way, way off the disk. And that's because there are literally hundreds of supernovae all going off in here at the same time. So you can see them actually individually in the radio. You can see them expanding even over time in the radio. So they're all quite young supernovae. There's been a whole load of these going off. And so all their remnants are working to push huge amounts of gas out of this galaxy. And if that keeps happening, and it might happen repeatedly as more interactions with its neighbors occur, then eventually all the gas in here will be cleared out. And here's another one where we can see these kind of plumes of hot gas being thrown out the middle of a galaxy where, again, a lot of supernovae have taken place. Okay, so that's the idea of gas-rich galaxies merging and will eventually form an elliptical galaxy. So, fortunately or unfortunately, our own galaxy is not going to be immune to this. The Andromeda Galaxy that we've been admiring and looking at nice pictures of is actually heading towards us. Okay, so unlike most galaxies, as we'll come to, if you measure the radial velocity of the Andromeda Galaxy relative to us here in the Milky Way, with the Doppler shift, then you measure a Doppler shift of minus 300 kilometers per second. So the minus means it's coming towards us, not going away from us. So you need a bit more information here. How do I not put that down? Let me just do that for you. Very distinct. 0.9 megaparsec. Okay. So the Andromeda Galaxy is nearly a megaparsec away, 0.9 megaparsecs, and it's coming towards us at this speed. So if you assume it's heading straight for us, so along that line of sight, how long before it collides with the Milky Way? Okay, so work out how long we've got left and come back after a bit.